Moving on into part two, where we look at the plate tectonics, volcanism, and the characteristics of volcanoes a little bit more in depth. Let's go back and take a look here at what we call a pluton. This is important because we have these magma chambers, these massive areas that we call batholiths. A pluton is something that is a magma reservoir that crystallizes beneath the Earth's surface or underground. And what happens is that we have these features that we can see coming from it. We have these magma chambers, this large magma chamber that's got these little spill-off pipes or conduits that are reaching the Earth's surface. So these are what we call dikes and sills, and we'll get into those here in just a few moments. Those are also plutons. But we look at batholiths. Batholiths are large plutons, these magma reservoirs that solidified into rock and over time were uplifted and brought to the Earth's surface. And these are granitic batholiths that really comprise the base of the North American continent and all continents. All continents are built upon these felsic batholiths. These are like the basis of which continents are formed. Well, there's smaller ones too, plutons, and these are what we call dikes and sills. And so if I look back at this network of igneous rock that was once existing, over time they cool and they crystallize and solidify, and then they uplift up to the Earth's surface. That's just a natural buoyancy. As we erode the surface, the material below is exposed. So pluton is a generalized term for solidifying beneath Earth's surface. That dikes and sills are named based on their orientation relative to the host rock. That a sill is a pluton that forms when liquid rock fills in the spaces that's between pre-existing rocks, or what I'll use the word parallel. This is called concordant, due to the solidifying parallel to sedimentary rock strata. So here where I see these parallel margins, the parallel ones are going to be my sills, and you can see it here in this picture. Whereas a dike is a pluton, I almost said crouton, wow, that cross-cuts through pre-existing rock. This is said to be discordant, that these move perpendicular. So the dikes are cutting through this pre-existing rock, whereas sills are laid down parallel to the pre-existing rock. So we'll find out that sedimentary rock strata is laid down in horizontal layers, where a sill is literally wedged in between them, whereas a dike cuts through them. So let's go back to the Ring of Fire. This is kind of a big ticket item. Considering we are talking volcanism, it's very, very difficult to get away from the fact that the majority of volcanism taking place on the Earth takes place in and around this area. It's a very active region because I have these plate boundaries. I have convergence taking place. I have hotspot volcanism taking place here. But because I have all these different boundaries, I have a lot of volcanic activity. So let's look at the three primary places in which we find volcanism. Convergent. If I have oceanic crust colliding with continent, so oceanic continental crust is going to lead to, this is a convergent boundary, volcanism. These are what we would call continental arcs. And when I have oceanic crust colliding with younger oceanic crust, the older is colder, therefore it's denser. It is what subducts. And this is what generates what we call volcanic island arcs. So we can have convergence of oceanic continental, oceanic oceanic, and later we'll find that is not volcanic. We'll find that continents can collide. Number two, divergent boundaries. Here we're still looking at just locations of volcanism, and this is the most common type of volcanism on Earth. Divergence. This is taking place where the oceanic crust, new and young oceanic crust, is finding its way to the Earth's surface all the time. And lastly, hotspot volcanism, and this is how the Hawaiian Islands form. We have this continual steady plume of hot rock coming from the mantle, and it's building the islands as the Pacific plate is moving kind of northwest. And here's a better picture, that these islands here, the Emperor Seamount, are now underwater landforms that they were once on the ocean surface and above, just like the Hawaiian Islands are today. So we've got these chains of features that were once volcanoes. So here's back to the convergent boundary volcanism. I just want to make sure we go back and we pay attention here as the land features, that these are volcanic systems that are commonly found where subduction is found. We find these volcanic chains, and when we start looking at the volcanic chains, you'll say, oh yeah, there is a characteristic pattern to them. That the Cascade Mountains in North America are reflective of this. And here we have, in Southeast Asia, we have these volcanic island arcs as well. and they're just what I'll just use the term land features. That the denser material is going to subduct, it's going to melt out. We studied this with Bowen's reaction series. Lower melting point minerals are going to rise, and these are the potential ingredients for very, very powerful eruptions. Here, if I move on to the next type of divergent boundary, we'll see that land features are characteristic of younger oceanic basaltic rock, right? Compositionally is mafic, is going to be younger here right at the divergent boundary, and we can radiometrically date this and find that it's older further from here. So we have a very nice sequential timeline as to what is taking place within the oceans, even though we cannot see them. It doesn't mean it isn't still taking place. And our last type of volcanism that we'll be studying is called intraplate volcanism, and we've kind of talked about this already with Hawaii. But we also have a hot spot in North America beneath Yellowstone National Park. That one of the hot spots is found beneath continental crust, which is going to lead to a compositional difference of magma, whereas one is beneath an oceanic plate. So the Hawaiian Islands are these very effusive, kind of low viscosity basalt flows, whereas in North America we have these rhyolitic composition, higher gas content, higher silica content, very explosive potential, and these are what we call, these are potential planet changers. So here I can take a look at the Pacific Northwest, and here's that chain that I can see where the Juan de Fuca plate is subducting beneath the North American plate. I get these very, well, let's just say they're powerful, but they're not necessarily game changers. They'd be pretty, well, they would not be fun to have take place in North America, but they're just kind of ticking time bombs. Whereas beneath Yellowstone, this is the result of these mantle plumes that are making their way to the Earth's surface, and these are game changers. So we've got two different features taking place, all within, you know, several hundred miles of each other, different types of volcanism taking place. Another type of feature that we can find where we have oceanic crust subducting beneath oceanic crust here, so I have subduction, are what are called these island arcs. And these are land features when two oceanic crusts meet. And we can actually find this here where we have, in Southeast Asia, where we have these islands of Southeast Asia here. And we can also find these where we find the Aleutian Islands. We have oceanic crust subducting beneath oceanic crust. So ultimately, and at the end of the day, I want you asking these questions. How and why do volcanoes erupt? We can talk about all the different kinds, but here's why. They have different temperatures, right? The magma itself is really hot, and hot is going to be buoyant, it's going to rise, so it finds its way to the Earth's surface, and that can lead to eruptions. But it also has a viscosity. The viscosity is when the magma reaches the surface. It depends on, well, let's just say the eruptions could depend on its viscosity itself. High viscosity magmas are going to lead to high pressure buildup of gases internally, going to lead to really violent eruptions. Where low viscosity, right, the runny magma, which would be like our basaltic magma, are going to be very, very mild eruptions. So the viscosity is a silica content, and therefore a gas content. The amount of gas it has is going to determine the nature of the eruption itself. So large amounts of gas and high viscosity form these game-changing, these caldera-forming eruptions. And these are what we'll be looking at in terms of these have changed and shaped biological evolution. So the role of heat and pressure. So the change in temperature at depth is known as the geothermal gradient. Lithospheric rock is solid, but it's still very hot. So one source of heat that leads to melting rock is just when the source originates from deep within the earth in the mantle. Right? Hot basaltic rock rises vertically, and we call this just a general plume. But rock can melt without the addition of heat. We call this decompression melting. This occurs as hot rock nears its melting point as it begins to rise. The lower pressure, coupled with the amount of water vapor, right, wet rock versus dry rock, contained in the magma further drives the rock to reaching its melting point. So as I decrease the pressure that's overlying it, it can melt, and it melts without the addition of heat. And this is what we're going to be looking at with Mentos and Diet Coke, and this is the lab you're going to be doing. And you're going to be creating this on your own. But it's really the process of what we call nucleation. This is where the pore spaces on the Mentos actually allow for carbon dioxide to come out of solution very quickly. And that's how and why we get these violent upward moving eruptions. That as the Mentos, it it physically reacts with the coke. It doesn't chemically react, and that's what a lot of people think is taking place here. So last couple topics here. Explosive eruptions. These are what blast debris that generate ashfall, pyroclastic flows, and pyroclastic surges. Explosive eruptions that can be potentially catastrophic, and they erupt. This is cubic kilometers of magma, just tremendous amounts of material. And these can lead to ash clouds very, very high up into the stratosphere. Notice we're not talking troposphere, we're talking stratosphere here. And they have severe environmental and climatic effects, and the fallout can become potentially damaging. Here we have a Mount Redoubt. This was in Alaska. Very, very cool looking eruption. And here was Tambora in 1816. It actually led to a year without summer. And this is what we call a negative forcing. It actually can create so much debris in the atmosphere that blocks out the sun. And then here are pyroclastic flows. Very, very cool. Imagine seeing that in your rearview mirror. And last but never least, and we'll look at the hazards here in just a moment, but we're kind of winding down here. You'll take a look here. We've got all this debris taking place. You're going to want to make sure you pay attention to the ashfall, the bombs, and here's how we can monitor what's taking place. We can measure the ground for deformation. We can measure if there are earthquakes, and we can also measure the gases that are emitted. And there you have the lecture